what we're going to do is do a couple different things for this process. One of them is going to be we're going to look at the MATLAB drive. So you should have your files in this. Once you've got your mobile sensor data files listed, I'm going to go ahead and pull down this one. This is the part where it's important to pay attention, because otherwise you'll get lost, right? Instead of having to go back and review it later. So we're going to tell it to keep the file because it's not actually harmful and going to cause things to explode. So then in your downloads, you will have some list of files. You should be able to find this one. So we're going to take that. We're going to cut that file from downloads, drop it back into Documents and MATLAB. So I'm going to drop it back in here because this is going to be a useful place for my purposes. You should have some kind of a file relevant to class probably, but then you'll have to remember this when you go into when you actually go into MATLAB. So you can do the same thing with the online version. Now, one of the things I'm going to have to do is, because I've relaunched this, you want to double check which directory you're in. You want to make sure you're under your Documents and then MATLAB. Otherwise, you need to change. You might have to go up a couple levels. You might even have to do the drop down over here and then go find where you're supposed to be so that you know exactly where you're located. Otherwise, you get lost, stuff gets lost or not included, and it causes all kinds of issues. So you want to right-click that file that you're interested in, and again, go back in, add it to path, selected folders and subfolders, because you want to include everything that's under that directory. So this particular one, the human gait data pull, this is what we're actually working with. So I'm going to close out some of these others because we don't need them. So this way we can kind of unclutter everything. We'll be doing a vibrations one that looks very similar to what we're doing here in the future. So we'll get lots and lots of practice of this process. So one of the things you will find is file name. Now there's the comment here explaining exactly what to do. You want to know what file name it is that you're using. So in this case, mine is called, this is whatever ends in .mat. So this is the walking_log1 is what I have it saved as. So you replace the word file name with the name of the file, strangely enough. I named it for maximum confusion there. So walking log 1. So walking log 1 is what we're loading. Then we're going to get some data out of it. That's going to pull in. This first part is clearing the command window and variables so that we don't have extra stuff cluttering our workspace. We load in using this load command that file name, and then what it's going to do is it's going to take this, and we create 3 variables: acceleration, x, y, and z. It's because we use the acceleration data set for this process, from the sensor logs. Acceleration is what we were tracking. If you track position, you'll have to go back and redo your data set. This is just part of the fun and excitement. We need the accelerations for x, y, and z because of how this relates to what we were doing in previous weeks with force equals mass times acceleration. This is the acceleration that we're interested in. So acceleration, all rows, first column is x, second column is y, third column is z. Another thing that you'll want to pay attention to when this actually loads in is the timing. So each of your sensor logs is going to be a little bit different in terms of total number of seconds. This has to be, there needs to be a time variable that is stepped in the same time size, the same time unit, tenths of a millisecond. This is, or tenths of a second, so 100 milliseconds here. What this is doing is sizing the time array to the same size as the data array that you're pulling in. So I want to say this one that I just did was something like 23.1 seconds, so we'll find out what that actual number is as soon as we load this in. So this stuff I'm going to pause at, and in order to make that easy, I'm actually going to set a what's called a breakpoint here. By setting a point, we're going to figure out what the length is, and then we're going to run up to the breakpoint, and we'll see what that sort of looks like. So we're going to use the run in advance or the run section. They're going to do the same thing. Run is going to do the same thing here. You'll learn more in the programming class about particulars of this. Then after this, we're actually going to be doing the plotting process, and we're going to see what this does, what it doesn't do, and what we need to change in order to make this plot the way that we want. Because we still have to learn a couple things. I can't do 100% of the work for you. So this is what we're going to do first. So I'll go ahead and run this. And we have our acceleration timetables and all of these things, except now we have to look at, under this acceleration timetable, what actually is the data range. So as soon as this actually loads up, here we go. So we have all of this data all the way down to, so we have 245 total step size, which is almost double this value. Almost exactly double, 124. So this needs to be increased, I believe, to 23.3. So what we're looking for is what the length of that variable is, and this will give us the first answer is what it's printing out there. So we haven't gone to some of the other ones. So we're going to step back out. All right, so we'll come back to the plots in just a second. I'm going to leave the same breakpoint there and say here, we're going to go ahead and run this first part. So 233, we're not quite there yet. And you can also figure out from this timestamp just how far it changes. So this is from 1536 or 1535, 36 down to 1536 even. So you can do some math on just exactly how many seconds this actually is. What we want is to make sure that this number for the time data is exactly the same size as the acceleration data, so that we aren't trying to plot two different lengths of arrays against each other, because that creates errors and confusion and all sorts of other things. So there's a number of ways that you can go about it. One of which is you can look at the length of time here, understand that it's a time step of about 0.1, and back figure. In this case, like I said, this is about 24.3 seconds or so. So I'm going to quit that debug run and see if I'm closer. Yep, just a couple shy. So 24.5. There we go. So 245 gives me the same size range as what we're doing. So this is one of the ways that I'm able to get this particular part calibrated so that my time array is the same size. This is why I need to know this information before I go to the next step. So this is something that's not obvious in the process that we're looking at. So one of the ways that you guys can do this with your data set is the same thing and go, okay, like I said, going backwards in math, because this has to be a 0.1 time step. Somebody who's really good at math, tell me what 245 times 0.1 is. 24.5. Good. Okay, a few of you are still awake. It's a good start. So 24.5. I went about this, the manual method, just to show you how you can get there a couple different ways. So if the size is 245 or whatever your size is for the data array, you need to calibrate the time data from 1 to that size. So there's a way that I could have automated this in the code. I chose not to, just so that you guys have some involvement in what this does. and actually got a chance to see how all of that works. So we've got the length of time. I'm going to remove this breakpoint because I no longer need it, and I can continue on to the actual plotting and then see what it does. So we have a couple pieces of information here. So we have 3 different plots. Now I've chosen 3 different colors to make it a little bit more obvious, but we have 3 different plots. How useful is this particular figure? Is it pretty easy to tell what's going on? Not so much, right? So what would be helpful to do? I mean, you could take an average, but an average will tell you something. There's a couple other things that we need to do. It would be a lot easier to analyze each of these if we separated them out, right? So how do we separate them onto multiple plots? That's one of the questions that we want to think about. So there's a lot of useful things, especially in the help, things like the plotting tools. Hey, we could take a look at their help documentation, and there's a bunch of information here as far as how to plot different things. One of the quickest way is to use this plot command, but the problem is when you need multiple plots, now you have to use a different sort of command. So instead of making you guys do tons of research, I'm simply going to suggest for now, what you actually want to do is you want to understand figures. Figures basically create a new window in order to do this. So you give it figure and then a name or a number, and this is really the easiest method. So you can click on these and see examples of what they're doing. So how we add this in, they'll give examples of how this is done. So we're going to give it, we can give it different names, and especially you can say figure name and then measured data, and then you can use all these different types. You can do running, walking, things like that. This is a quick and easy modification to be able to make. You can just call it 1 or 2. You can turn the number off if you want. There's lots of different things that you can configure and do fancy stuff later. We're also going to do a little bit of data analysis in Excel, so that you don't have to learn all of the mechanics of how to run this and operate all of the data analysis in MATLAB right now. So we've already created the variables and things that you guys are familiar with. So each of these, if you were to open each of these up individually, you would find that these tables you can copy over into Excel and work that way. So we're going to do that for some of the plots that you guys are going to be generating, just so that it's easier for you guys to do the analysis instead of trying to do a ton of plotting in MATLAB right now. So we'll learn some of the cool tricks later. All right, so we have acceleration in the X, the Y, and the Z. For all of those, we have our plotting tools. Where are we going to start adding in the figures? Right before we start doing the plotting. So this is really about the only changes that you need to make to this particular code set. So the syntax looks like this. Figure, and then I'm probably going to go ahead and do name, and then give it a particular name. And again, you want to think, if you are lost or not remembering what it is that you had just looked at, you're struggling with what the MATLAB syntax looks like, open back up the help and go back and read back over it. Look at what's actually being used. So a lot of things in MATLAB, general rule of thumb, you're doing single quotes for. There's a whole bunch of reasons behind that. We're not going to get into them, but this is what you want to pay attention to, is what does the syntax look like. So you can even change the colors and do all sorts of wild, crazy things. For now, we don't need those. We just need to have a figure name. So this is going to be walking X. So this we can now copy. You want to make sure that you have the suppression on for most of what you're working on. The hold on, we don't really strictly need. It's something that will be helpful. So we'll go ahead and add this block as well to the other plotting tools. So first, we're going to copy the figure name. We're going to change it for each one of these and update these. And so this will be walking in Y. This will be walking in Z. And there we go. So walking in Z. So each of these is going to be included. I'm going to go ahead and add in the X and Y labels because these are things that we need to know something about. What you'll also notice is that the plots that MATLAB can generate as we walk through some of this, we can use a lot of this data in Excel just as easily as MATLAB and some of the other things. This is helpful in order to develop multiple plots. So I'm going to make sure the other plot is closed at the moment. I'll go ahead and run this. And what we will have is we will have our three figures for the X, the Y, and the Z. Now, this is a little easier to answer or a little easier to analyze because now you can at least see what's happening. So the real question is, what was I doing? A couple of you saw me taking the data set. The question is, can you figure out what's happening from this information?
Like each step kind of?
So each of these peaks is some kind of a step event, right? So this is the kind of thing that we're looking at, right? In a steady state, right, there's a little bit of kind of a ramp up time. Then there's a sort of steady state, like an average of high peaks and low peaks, right? And depending on how fast you're trying to move, what would you expect those amplitudes to be? Would you expect them to be larger or smaller?
Larger.
You'd expect them to be larger, right? Why?
Moving faster.
You're moving faster, you're trying to cover the same distance, the same arc in a compressed amount of time, right? So what has to be higher? Both your velocity and your acceleration, right? So as you go to do something like running, this becomes very, very important so that you can observe just how far those peaks are separated, right? So especially those of you that are on any of the athletics team, you can actually start using this kind of information and say, hey, coach, there's this cool thing that my professor did, this crazy engineering professor, and I can now look at like what my accelerations are when I strap my phone to myself and run around the track, right? I mean, that sounds like fun, right? But you can actually get data and compare from run to run and see if you are in fact using more energy or if you're running out of energy and track what your performance is back to back, right? So maybe you shouldn't tell your coaches about this because then they'll actually get really excited. And so that could be a problem for you. So what about here in the Y? What's happening in the Y-axis? Take out your phones real quick and look at what the actual data is on the Y acceleration and the X and the Z and see what the actual sensor log looks like. Which one's which? You got to know. So if you're holding your phone steady and you're seeing what's happening as you tilt in the X and the Y, tilt the different axes and see what happens to the acceleration numbers. Which one's which? So which one's changing drastically as you move up and down, as you move side to side, right? Because you think you know which one's which, but until you know for sure what's happening, which axis is which? right? This is important to understand because then you can map, oh, that one's this direction. Then you have to think about which orientation was the phone in and what was it doing, right? So you think it's X and Y and Z, but is that actually what you're observing? And that's part of what you have to figure out. So one of them has much lower intensity overall peaks, but some of them have much higher intensity peaks. So what about this? A couple of these peaks down here are on the order of minus 35 meter per second squared. Well, wait a minute. What's gravity again? 9.81. So somebody who's good at math, tell me from 35 minus 35.34, what's that ratio to gravity? How many G is that? Somebody do some quick math. So on the order of 3.6 times gravity, right? So that's a lot, right? How many of you guys thought just walking around you could see that kind of G in deceleration? Is that a little different way of thinking about things, right? You thought fighter pilots are impressive. Well, walking is pretty neat stuff, right? So they're like, 12 Gs. Yeah, no, you don't, man. Sure, you weren't conscious for that. Not 12 G, sorry. The point is, this is an actual measurement that came off of that device, right? And so long as, if you made the terrible mistake of wearing shorts today, you have a very good sense of whether or not the phone was actually moving, right? Being fixed with masking tape and all. But if the phone wasn't moving relative to your frame of reference, one of those axes actually may have experienced multiple G of acceleration. So how much force is that? That's what you have to figure out, right? Because you think about for a second, one of those impact events is all of your weight landing on that heel. So is that maybe why your heel is a really thick bone compared to everything else in the body? I mean, it could be that way on purpose. It's a weird concept, right? Could be that way on purpose. So these are some of the things you want to think about in your data set, right? What are some of these peaks? What are some of the averages? And then you can take this data over into Excel and do the same kind of plotting. But what you also want to do is you want to do some calculations from this in order to understand what the actual forces are from some of these accelerations. So what are the peak forces that you get, positive and negative, in each of these kinds of events, right? Because it's very clear that each one of these is a step event. But you'll also notice that if you try and overlay them in terms of timing, this is why that singular plot is also helpful, is when you go to overlay them in timing, what you're going to find is they don't all overlap. These peaks happen at different timings compared to each other. Why do you guys think that is?
Like factors that was like,
Yeah, what you're doing is you're seeing an intense peak as you step down. You have one of these intense negative peaks, right? Then you have, as that force resides and comes back towards whatever the baseline is, right? Because we talked about gravity being something like minus 9.81. Well, if you took an average straight across all of these, what do you think you're going to find it at? Probably somewhere just a little bit below minus 10. Does that sound about right for gravity? So gravity's there, and it's in your data. So it's real, it's not imaginary, right? It's not an agreed upon concept. This is why in science we like to measure stuff. We don't get in a room and vote, oh yeah, I think this is the science. It's not actually how stuff works. So this data tells you a lot of things. Here, the acceleration in the X, this becomes pretty important because depending on how your phone is positioned, right? If your phone is on the front of your thigh for this experiment, then your X and Z are going to have a little different relationship. So these are things that you want to be thinking about. So Z is a little bit more stable and a little bit less peaky overall, but there's still some amount of movement. In the X, you have some very distinct, clear events, right? So you want to start thinking about, okay, if that's part of the leg swinging is the X-axis, you would expect a really intense Y to hit, and then the X would happen because the X would change, right? So you'd expect them to be offset back and forth as you're walking, and that's part of what we're seeing in the data here. So I want you guys to get some kind of an average of what's the overall average acceleration, and that tells you, are they generally moving in what it considers to be a negative direction or a positive direction in X? And then some of these other factors. You want to observe, hey, we actually do seem to have gravity plus other events in the Y. And all of these things you want to start talking about and analyzing in your report so that you can compare, especially as you go to calculate, what are the peak forces and average forces, both positive and negative, in X, Y, and Z. What do those correspond to with different parts of this gait process, this human gait process, and how do these go into, how do these actually get used in understanding what's going on, right? So if you didn't have an even pattern and you had something like a higher peak, a lower peak, a higher peak, a lower peak, and it was almost sinusoidal in behavior, what do you think that would be indicative of, for instance? You're running strange, maybe, right? So if someone, for instance, had an injury and they were hobbling a little bit, right? That would be a thing that could happen. What happens to their gait? It changes, right? You want to spend a lot less time on the foot that has pain, right? So that's something called an antalgic gait. That's something you guys can look up. That's your new $5 word for the day, antalgic gait, something that is associated with pain. So the process you would expect is they would have a higher peak, lower peak, higher peak, lower peak, but the higher peak would be which one? Which one would you expect the higher accelerations to be in of the two? Would it be the good foot or the injured foot? The injured foot. Why? You want to spend less time on it. You want it down and back as fast as you can, right? So you're going to have higher intense peaks on the weaker side or the side that's hurting, right? So these are some of the things that you want to be thinking about as you go through this analytic process and start looking at what additional kinds of information is there in the data and what would that look like? What would I expect to see versus what do I actually see? So those are some of the considerations that I want you guys to have as you go through the actual analysis of this.